Hello there, and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe you've been wondering about the cosmos, or maybe you simply need a place to let your thoughts drift into something vast and gentle. Either way, you're exactly where you need to be. Tonight, we're traveling to the most distant reaches imaginable, to the edge of the universe itself. Not with rockets or telescopes, but with quiet curiosity and the soft glow of wonder. We'll explore what it means for something to have an edge, what lies at the boundary of everything we know, and what mysteries wait in that impossible distance. Some of what you hear may reshape how you see the night sky. Other facts might simply wash over you like waves on a shore, present for a moment, then gently receding. And if this peaceful journey helps you find rest, consider liking and subscribing. It helps others discover this quiet corner of wonder too. I'd love to know where you're tuning from and what time it is there. It's fascinating to see how these videos connect people from around the world. Now, let your shoulders drop. Let your breathing slow, and let's begin this gentle drift toward the edge of everything. The observable universe has a horizon we can never cross. When we talk about the edge of the universe, we're really talking about the edge of what we can see. This boundary is called the cosmic horizon, and it sits roughly 46 billion light years away in every direction. Beyond that line, light hasn't had enough time to reach us since the Big Bang. It's not a wall or a border. It's simply the limit of visibility, like standing on an ocean and watching the horizon curve away. There may be more universe beyond it, perhaps infinitely more, but those regions remain forever hidden from our view. The horizon expands as time passes, but the universe expands faster. Some parts of space are racing away so quickly that their light will never reach us, no matter how long we wait. They exist, but they are unreachable, drifting beyond the edge of possibility itself. Light from the edge takes longer to arrive than the universe is old. Here's something strange. The universe is about 13.8 billion years old, but the light we see from the most distant galaxies has traveled for more than 13 billion years, and yet those galaxies now sit 46 billion light years away. How is that possible? The answer lies in expansion. While light was traveling toward us, space itself was stretching. The galaxy that emitted the light was much closer when the photons began their journey. But over billions of years, as those photons crossed the growing void, the universe expanded beneath them. By the time the light reaches our telescopes, the source has drifted far, far beyond where it was. Distance and time don't match in an expanding cosmos. The edge moves even as we watch. The universe may have no edge at all. What if there is no edge? What if the universe simply curves back on itself, like the surface of a sphere? This is one possibility cosmologists consider. If space is curved in just the right way, you could travel in a straight line forever and eventually return to where you started, never encountering a boundary. It's hard to imagine, but it's similar to walking around the Earth. You never fall off because there is no edge, just curvature. Current measurements suggest the universe is either flat or very nearly so, which would make it infinite. But if it has even slight curvature, it might be finite yet unbounded. A cosmos with no beginning, no end, and no edge. Just gentle, endless folding back into itself. Some galaxies are moving away faster than light. Einstein told us nothing can move through space faster than light, and that's still true. But space itself isn't bound by that rule. In the farthest reaches of the universe, galaxies are being carried away by the expansion of space at speeds that exceed the speed of light. They're not racing through space. Space is stretching between us and them. This means there are galaxies we can see now whose light will never reach us again. They've already crossed a threshold, a point of no return. Eventually, they'll fade from view entirely, not because they died, but because the space between us grew too vast. The universe is not just expanding, it's accelerating. And with each passing moment, more of it slips beyond our grasp. The cosmic microwave background marks the furthest we can see in time. There's a wall of light surrounding us, not a physical wall, but a glowing shell of ancient radiation called the cosmic microwave background. It comes from a moment roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. Before that, the universe was an opaque fog. We cannot see through it, no matter how powerful our telescopes. This faint glow is the oldest light in existence, stretched by expansion into microwaves. It fills the entire sky, uniform and soft, a relic of the universe's infancy. In a sense, this is the true edge of our visible past. Beyond it lies only darkness and theory. We live inside a bubble of visibility. Imagine you're standing in the center of a vast sphere. Everything inside that sphere is visible to you. Everything outside is not. That's where we are. Earth sits at the center of the observable universe, not because we're special, but because observation is always centered on the observer. Every point in the universe has its own observable sphere. An alien on a planet 10 billion light years away would see a completely different set of galaxies. Their edge would not be ours. Their horizon would not match. We all live inside our own bubbles of light, shaped by time, distance, and the speed at which information can travel. The universe may be infinite, but what we can know is not. The edge is always moving. The cosmic horizon isn't static. It grows. Every second, light from slightly more distant regions reaches us for the first time. New galaxies flicker into view at the edge of detection. But this growth is slower than you might think. While the observable universe expands, the acceleration of space means that we're also losing galaxies at the far edge. They slip away faster than new ones arrive. In the distant future, billions of years from now, observers in our galaxy will see a much emptier sky. Entire clusters will have vanished beyond the horizon. The universe will appear smaller, lonelier, even as it grows. The edge is not fixed. It breathes, shifts, and changes with the passage of time. There may be infinite copies of you beyond the edge, if the universe is truly infinite. As some models suggest, then the possible arrangements of matter are also infinite. That means somewhere, far beyond what we can see, there might be another version of you, not metaphorically, literally. The same atoms, the same choices, the same life. In an infinite cosmos, every possible configuration must occur not just once, but infinitely many times. There could be planets identical to Earth, galaxies identical to the Milky Way, and people identical to you, living lives that mirror your own or diverge in subtle ways. It sounds like science fiction, but it's a logical consequence of infinity. You are unique here, but out there, beyond the edge, you may exist again and again, endlessly reflected in the vast mirror of space. The universe has different edges depending on what you're looking for. There isn't just one edge. There are many. depending on what you mean by edge. The particle horizon marks the farthest distance light has traveled since the Big Bang. The event horizon marks the farthest we will ever be able to see, even in the infinite future. The Hubble sphere marks where space expands at exactly the speed of light. Each of these boundaries sits at a different distance, and each tells a different story about the universe's structure and fate. Some are growing, others are fixed, some we can see, others are purely theoretical. The edge of the universe is not one line, but a series of nested boundaries, each revealing something new about the cosmos and our place within it. Dark energy pushes the edge further away. Something is driving the universe apart. We call it dark energy, though we don't really know what it is. It acts like a repulsive force, embedded in space itself, causing galaxies to accelerate away from each other. The more space there is, the more dark energy there is, and the faster everything moves apart. This means the edge of the observable universe is not just drifting, it's being actively pushed. Dark energy makes up roughly 68% of the universe's total energy. It's invisible, mysterious, and relentless. And because of it, the distant future will be lonelier than the past. Galaxies beyond our local group will disappear, the sky will darken, and the edge will retreat into an unreachable distance, leaving us in an island of light surrounded by an ocean of expanding night. We can see galaxies that no longer exist. When you look at the most distant galaxies, you're not seeing them as they are. You're seeing them as they were billions of years ago. The light you observe left those galaxies when the universe was young. In the time it took that light to reach us, those galaxies have changed, evolved, maybe even merged with others or faded entirely. The galaxies we see at the edge of the universe are ghosts, snapshots of youth frozen in light. They may not exist anymore, at least not in the form we observe. This is the strange nature of cosmic observation. The further you look, the deeper into the past you see. Telescopes are time machines. And the edge of the universe is also the edge of history. Some light will travel forever and never be seen. Not all light finds an observer. Photons are released constantly from stars, galaxies, and quasars in every direction. Most travel through the void without ever hitting anything. Some will journey for trillions of years, crossing unimaginable distances, and still never encounter a planet, a telescope, or an eye. In the expanding universe, many photons are doomed to eternal solitude. They race through the dark, stretched into invisibility by cosmic expansion, fading into wavelengths too long to detect. These lonely travelers carry information about their sources, stories that will never be read. Somewhere beyond the edge, light is still traveling, still hoping, still moving toward a destination it will never reach. The farthest galaxy we've seen existed just after the Big Bang. Using the James Webb Space Telescope, astronomers have glimpsed galaxies that formed less than 300 million years after the Big Bang. That's astonishingly early. These galaxies are small, dense, and burning with the light of young stars. Their light has been traveling toward us for over 13 billion years, stretched by expansion into deep red wavelengths. What's remarkable is that they exist at all. Cosmologists didn't expect galaxies to form so quickly. These ancient systems challenge our models. They suggest the early universe was more active, more dynamic than we imagined. Observing them is like looking at childhood photographs of the cosmos itself, fuzzy, faint, and full of wonder. They sit near the edge of everything we can see, glowing softly in the infrared, whispering stories of a universe just learning how to shine. There's a region of space we can see but can never reach. Some galaxies are visible to us now, but we'll never be able to visit them, even with infinite time and faster than light travel. Why? Because the space between us and them is expanding too quickly. Even if we left today at the speed of light, we'd never close the gap. The destination is receding faster than we can approach. This region, beyond the Hubble sphere, is observable but unreachable. We can study it, we can photograph it, but we can never go there. It's a one-way mirror. We see them, but any signal we send will never arrive. They exist in our universe, but not in our future. It's a strange and humbling boundary, drawn not by walls, but by the geometry of space-time itself. Space might be infinite in some directions, but not others. What if the universe doesn't have the same shape in every direction? Some cosmological models suggest space could be anisotropic, meaning it might stretch differently depending on which way you're looking. In one direction, it could be infinite. In another, it might curve back or end in some exotic topology. Current observations show the universe appears roughly the same in all directions, a property called isotropy. But small deviations exist, subtle patterns in the cosmic microwave background that hint at asymmetry. If space is truly anisotropic, the edge might not be the same distance away in all directions. The universe could be lopsided, stretched, or twisted in ways we're only beginning to understand. And what we call the edge might be more complex than a simple sphere. The Big Bang wasn't an explosion in space. It's tempting to imagine the Big Bang as a fireball expanding into empty space. But that's not quite right. The Big Bang wasn't an explosion in space. It was the expansion of space itself. There was no center, no edge from which it burst outward. Every point in the universe was part of the beginning. Space didn't expand into anything. It simply grew, carrying matter and energy with it. This means there's no location you can point to and say, that's where it all started. The Big Bang happened everywhere, and the edge of the universe, if it exists, isn't the remnant of some initial boundary. It's just the limit of how far light has been able to travel since time began. A horizon, not a birthplace. We may be living in a multiverse. Some theories suggest our universe is just one bubble in a vast cosmic foam. Inflation, the rapid expansion that occurred fractions of a second after the Big Bang, may have created countless other universes, each with its own laws of physics, its own particles, its own edge. These universes don't touch. They don't interact. They exist in separate pockets of space-time, forever isolated from one another. If this is true, the edge of our universe is not the edge of reality. It's just the boundary of one chapter in an infinitely larger story. We may never be able to prove the multiverse exists, but the math allows it, the physics suggests it, and somewhere beyond our edge, other edges may surround other skies, other stars, and other sleepers wondering if they're alone. Time itself may end at the edge. In general relativity, space and time are woven together into a single fabric called space-time. And if space has an edge, time might too. Near the boundary of the universe, where expansion accelerates and strange physics might take hold, the flow of time could become distorted or even stop. This isn't proven, it's speculative. but some models suggest that at the very edge, causality breaks down. Events might not follow one another in the usual way. Clocks might tick differently, or not at all. To an observer at that boundary, assuming one could exist, the universe might look frozen or moving in reverse. Time as we know it is tied to the structure of space, and if space ends or changes fundamentally, time might follow. The coldest place in the universe might be at the edge. The further you travel from stars and galaxies, the colder it gets. Deep in intergalactic voids, far from any source of heat or light, temperatures approach absolute zero. These regions are among the coldest natural places in existence, cooler than the cosmic microwave background itself in some localized spots. At the edge of the observable universe, where galaxies thin out and the ancient glow of the Big Bang fades, the cold deepens. Matter becomes sparse, energy dilutes. What remains is stillness, silence, and a chill that no fire can touch. In the distant future, as the universe continues to expand and cool, these cold voids will grow. Eventually, much of the cosmos will become a frozen desert, dark and empty. But for now, the edge is simply quiet, waiting in the cold. The universe's expansion is accelerating. For most of cosmic history, gravity slowed the expansion of the universe. Galaxies pulled on each other, resisting the outward push. But about 5 billion years ago, something changed. The expansion began to speed up. This acceleration is driven by dark energy, a mysterious force we don't yet understand. It acts like anti-gravity, pushing space apart faster and faster. The more the universe expands, the more dark energy there is, and the stronger the acceleration becomes. This means the edge of the observable universe is not only moving away, it's moving away faster over time. In the far future, galaxies will recede so quickly that new light will stop reaching us entirely. The sky will empty, the edge will retreat, and the universe will grow into a vast, lonely expanse where even light cannot bridge the gaps. Quasars at the edge shine brighter than entire galaxies. Near the edge of the observable universe, we see quasars, brilliant beacons powered by supermassive black holes. These objects are among the most luminous in existence, outshining entire galaxies despite being concentrated in a region smaller than our solar system. They formed when the universe was young, fed by vast reservoirs of gas spiraling into black holes at the centers of ancient galaxies. The light from these quasars has traveled more than 12 billion years to reach us. In that time, the universe has changed dramatically, but the quasars remain frozen in our view, glowing with the intensity of youth. They mark the distant edge, signposts in a cosmic wilderness. To see them is to witness the universe in its adolescence, wild, energetic, and blazing with untempered light. There's a wall of galaxies at the edge of our local universe. Our galaxy, the Milky Way, is part of a larger structure called the local group, which itself is part of the Laniakea supercluster, a vast web of galaxies stretching across 500 million light years. At the edge of this structure lies a boundary, not of space, but of gravitational influence. Beyond it, galaxies are pulled by different superclusters. In one direction, we're being drawn toward the Great Attractor, a massive concentration of mass. In another, we're pushed by the dipole repeller, a vast cosmic void. These boundaries aren't visible walls. They're subtle shifts in motion, flows in the cosmic web, but they define the edge of our gravitational neighborhood. Past them, we enter the domain of other forces, other attractors. The universe is not random. It's structured, layered, and bordered by invisible lines of pull and push. The universe could be a hologram. It sounds like science fiction, but some physicists take it seriously. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, like a 2D surface containing a 3D image. If this is true, the edge of the universe might hold all the information about everything inside it. We experience 3 dimensions, but the fundamental reality could be written on a distant 2-dimensional shell. This idea comes from black hole physics, where the event horizon appears to store information about everything that falls in. If the same principle applies to the universe, then the edge isn't just a boundary, it's a screen. And we, along with stars, planets, and galaxies, might be projections, shadows cast from a deeper layer of reality we can't directly perceive. Light from the edge is stretched into invisibility. As light travels across billions of years through expanding space, it gets stretched. Visible light shifts into infrared, then microwaves, then radio waves. At the very edge of the observable universe, light has been stretched so much that it becomes almost impossible to detect. What was once blue light from a young star might arrive as a faint microwave signal, indistinguishable from the background hum of the cosmos. This stretching is called redshift. The greater the distance, the greater the shift. Galaxies at the edge are redshifted to the point where their light is barely above the noise. They exist on the threshold of visibility. A little further, and they vanish completely, swallowed not by darkness, but by expansion itself. They fade into wavelengths our instruments can no longer read, whispers that dissolve into silence. We are made of atoms born near the edge of stars. Every atom in your body, except hydrogen, was forged in the heart of a star, or in the explosive death of one. Carbon, oxygen, iron, calcium, all were created through nuclear fusion deep inside stellar cores. When massive stars die, they scatter these elements across space in supernova explosions. Over billions of years, those atoms drift, mix, and eventually coalesce into planets and people. Some of the atoms in your body may have come from stars near the edge of the galaxy, or even from material ejected by stars in distant galaxies long ago. You are not separate from the cosmos. You are made of it. The edge of the universe may be far, but the elements that compose you have traveled from distant places, ancient fires, and long-forgotten explosions. You are stardust, and the edge is part of your origin story. The cosmic web stretches all the way to the edge. Galaxies are not scattered randomly through space. They're arranged in a vast network of filaments and voids called the cosmic web. These filaments, made mostly of dark matter and gas, stretch for hundreds of millions of light years, connecting clusters of galaxies like threads in a tapestry. At the larger scales, the universe looks like foam or a neural network with dense nodes and empty spaces in between. This structure extends all the way to the observable edge. Even the most distant galaxies we see are part of this web, tracing the same patterns that govern our local universe. The cosmic web is the skeleton of the universe, a hidden architecture shaped by gravity and time. And the edge, far from being empty, is woven into the same vast, intricate design. The first light ever released still surrounds us. When the universe was 380,000 years old, it released its first light. The cosmic microwave background That light has been traveling ever since, filling all of space. But here's the thing, it didn't come from one place. It came from everywhere. At that moment, the entire universe glowed, and as space expanded, that glow stretched and cooled. Today, it surrounds us as a faint, uniform radiation. No matter which direction you look, you see the same ancient light, now shifted into microwaves. This glow is the closest thing we have to a visible edge in time. It marks the moment the universe became transparent. Before it, there was only fog. After it, there were stars. The cosmic microwave background is a shell of light wrapped around everything we know, soft, old, and ever-present. Some theories suggest the universe has a mirror edge. What if the universe doesn't just end or loop, but reflects? Some speculative models propose that the cosmos might have a mirror-like boundary where particles and light could bounce back. If true, distant light could return to us, creating ghost images of galaxies or even of ourselves, seen from impossible angles. This isn't mainstream physics, but it's an intriguing thought experiment. A reflective edge would create strange symmetries, repeating structures, and echoes across space-time. We don't see evidence for this. The universe appears transparent and open. But in the realm of theory, where imagination meets mathematics, even mirrors at the edge of reality are not entirely ruled out. And in the quiet dark, perhaps the cosmos looks back. The observable universe is just a tiny fraction of the whole. If the universe is infinite, then what we can see is nothing, a droplet in an endless ocean. Even if it's finite, the observable portion may be only a small piece. Some estimates suggest the full universe could be thousands or even millions of times larger than what we can observe. We'll never know for certain, because light from those regions hasn't reached us and never will. But it's humbling to consider. Everything we've ever studied, every star, every galaxy, every distant quasar, is just the beginning. Beyond our horizon lies more, perhaps infinitely more. Not void, but worlds. Not silence, but song. The edge we see is not the end. It's just the limit of our vision. Ancient galaxies look younger than nearby ones. When we observe galaxies near the edge of the universe, we're seeing them as they were billions of years ago. And they look different. They're smaller, bluer, more chaotic. Star formation is rampant. Structure is still forming. These are not the mature spirals and ellipticals we see nearby. They're adolescent systems, full of energy and activity. Over billions of years, they've grown, merged, and settled into the shapes we recognize today. But we don't see that evolution. We see only a snapshot, frozen in the light that left them long ago. The edge of the universe is also a window into youth, a gallery of the cosmos in its formative years. What we see there is not what exists now. It's what was, preserved in light, glowing softly across time. The edge might mark where physics changes. Could the laws of physics be different at the edge? Some theories suggest that the fundamental constants, like the speed of light or the strength of gravity, might vary across space. If true, regions far beyond our observable horizon could operate under slightly different rules. Stars might burn differently. Atoms might be structured in unfamiliar ways. This is speculative, but not impossible. If the universe is truly vast and varied, there's no guarantee that the physics we observe here applies everywhere. The edge, then, might not just be a boundary of distance. It could be a boundary of reality itself. Where the familiar gives way to the strange, and the rules we know begin to bend or break, we may never know. But the possibility remains quiet and unsettling at the far reaches of thought. Inflation pushed the edge far beyond what we can see. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. Space grew faster than the speed of light, doubling in size many times over in an instant. This rapid growth pushed much of the universe far beyond what we'll ever be able to observe. What was once close enough to see was suddenly separated by unimaginable distances. Inflation solved several cosmological puzzles, but it also created a mystery. If it happened, then the observable universe is just a small patch of a much larger whole. The true edge, if there is one, lies far beyond our horizon. We're living in the aftermath of that ancient burst, surrounded by a universe we can only imagine, never see. The universe was once small enough to hold in your hand. Rewind time far enough, and the entire observable universe, everything we can see today, was compressed into a region smaller than an atom. At the moment of the Big Bang, all of space, matter and energy occupied a single point, a singularity of infinite density and temperature. Then, in an instant, it began to expand. Within fractions of a second, it grew to the size of a marble, then a city, then a galaxy. The expansion continues today, slower but relentless. That tiny seed has become a cosmos spanning billions of light years. The edge we talk about now was once no distance at all. Everything was touching. Everything was one. And in a sense, it still is. The universe has grown, but it hasn't moved into anything. It simply became larger, carrying the memory of that impossible smallness with it. Time runs differently near the edge. Due to the effects of general relativity and the expansion of space, time doesn't flow uniformly everywhere. In regions of intense gravity, near black holes or massive galaxy clusters, time slows down relative to less dense areas. At the edge of the observable universe, where space is expanding rapidly and conditions are extreme, time may behave strangely. To a distant observer in such a region, our galaxy might appear frozen or moving in slow motion. Similarly, if we could somehow observe a clock at the edge, it might seem to tick at a different rate. Time is not absolute. It bends, stretches, and shifts with the fabric of space. And at the farthest reaches, where physics pushes into the extreme, time itself becomes part of the mystery. Gravitational waves reach us from near the edge. When black holes collide or neutron stars merge, they send ripples through space-time called gravitational waves. These waves travel at the speed of light, stretching and squeezing space itself as they pass. We've detected dozens of these signals, and some originated billions of light years away, near the edge of what we can observe. Gravitational waves carry information that light cannot. They pass through matter and dust without scattering, offering a new way to explore distant events. As our detectors improve, we may soon pick up waves from even closer to the edge, from the universe's earliest violent moments. These ripples are whispers from across the cosmos, faint echoes of cataclysms that happened before the sun was born. And they're still arriving, traveling silently through the dark. The darkness between galaxies isn't empty. Look at the night sky, and the spaces between stars seem empty. But zoom out further, and even the spaces between galaxies are full of something. Thin wisps of hydrogen gas, stray photons, cosmic rays, dark matter, and perhaps particles we haven't discovered yet. This intergalactic medium is incredibly sparse, just a few atoms per cubic meter, but across vast distances it adds up. It absorbs light, scatters signals, and plays a role in cosmic evolution. Near the edge of the observable universe, this medium becomes even more important. It's the scaffolding on which structure forms, the invisible glue holding the cosmic web together. The darkness is not empty. It's full of potential, full of quiet presence, waiting to be understood. Every point in the universe is the center. There's a strange truth about cosmology. Every observer sees themselves at the center of the observable universe. That's not because they're special. It's because observation is always centered on the observer. The light reaching you has traveled from all directions equally, forming a sphere with you at its middle. An alien on a distant planet sees the same thing, with themselves at the center. There is no universal center, no privileged position. The universe has no middle because it has no edge, or if it does, we can't see it. Every place is the center of its own horizon. Every star, every galaxy, every quiet planet. In this sense, you are at the center of the universe, and so is everyone else. The universe's temperature is dropping. Since the Big Bang, the universe has been cooling. At the beginning, temperatures were unimaginably high, trillions of degrees. As space expanded, that heat spread out and cooled. Today, the average temperature of the universe is about 2.7 Kelvin, just a few degrees above absolute zero. This is the temperature of the cosmic microwave background, the faint glow left over from the early universe. Over time, as expansion continues, the temperature will drop even further. In trillions of years, the universe may approach absolute zero, becoming a cold, dark, and nearly empty expanse. The edge of the universe is already among the coldest places in existence. And as time goes on, the warmth of creation will fade entirely, leaving only stillness. Some photons have been traveling since before Earth existed. The light we see from distant galaxies left its source billions of years ago. Some photons reaching us today began their journey before our solar system formed. They traveled through expanding space for eons, crossing voids, passing through intergalactic gas, and finally arriving at a small blue planet where a telescope waits. These photons carry stories, encoded in their wavelengths, about the stars that emitted them, the gas they passed through, and the expansion they endured. They are travelers, older than mountains, older than life itself. And when they finally reach your eye or a camera sensor, their journey ends. A silent arrival after billions of years. Information delivered across time from a universe that no longer exists in the form we see. We may never know what lies beyond the edge. There are limits to knowledge. Some questions may never have answers. What lies beyond the edge of the observable universe? We don't know. We may never know. If those regions are moving away faster than light, no signal from them will ever reach us. If the universe is infinite, there's no edge to find. And if it's finite but curved, the boundary might be unreachable in principle. Science has brought us far, but it cannot take us everywhere. Some mysteries remain, not because we lack the tools, but because the universe itself imposes limits. The edge, whether real or conceptual, marks the boundary of the knowable. Beyond it lies not darkness, but uncertainty, a place where wonder meets humility, and imagination must carry us further than data ever can. The edge is where new galaxies first became visible. Right now, somewhere at the edge of the observable universe, a galaxy is crossing into view for the first time. Its light, traveling for billions of years, is just now reaching the boundary of what we can see. We haven't detected it yet. Our telescopes may never be sensitive enough to spot it. But it's there, flickering into existence at the very limit of observation. Every moment, new light arrives from further away. The edge is not a static line, but a growing frontier. As time passes, we see deeper, further, older. Each new observation pushes the boundary outward by tiny increments. But the expansion of space pushes back, carrying distant galaxies away faster than their light can reach us. It's a race between light and space, and at the edge, that race plays out in the birth of visibility itself. Black holes at the edge might be evaporating. Black holes lose mass slowly through a process called Hawking radiation. For most black holes, this loss is negligible. They absorb more mass and energy than they radiate. But at the edge of the universe, in the deep cold and emptiness of the far future, black holes might begin to truly evaporate. With no nearby stars or gas to feed on, they'll slowly emit energy, shrinking over trillions of years until they disappear entirely in a final flash. This process hasn't happened yet. The universe isn't old enough, but near the edge of time, it will. Black holes, the most enduring objects we know, will eventually fade into radiation. Even gravity's strongest grip will loosen, and in the end, nothing remains but the soft glow of particles released into the void, the last whispers of matter dissolving into light. The cosmic web ends in giant voids. At the larger scales, the universe is structured like a sponge. Dense filaments of galaxies surround vast, empty regions called cosmic voids. These voids can span hundreds of millions of light years and contain very little matter. At the edge of the observable universe, these voids become more pronounced. Galaxies cluster along the filaments, but between them lies emptiness, deep and silent. If you could stand inside a cosmic void, you might see no galaxies at all in any direction. Just darkness and the faint glow of the cosmic microwave background. These voids aren't empty in the absolute sense. They contain dark matter, stray atoms, and traces of ancient light. But compared to the dense regions, they're deserts. Quiet, cold, and still. The edge of the universe is not just where things end. It's where space opens into its most profound solitude. Time began at the same moment everywhere. There's no place in the universe that's older than anywhere else. Time itself began with the Big Bang, and it began everywhere at once. Every point in space shares the same cosmic age, roughly 13.8 billion years. This might seem strange because we observe distant galaxies as they were in the past, but that's a trick of light, not time. Those galaxies exist now, just as we do, in the same moment of cosmic history. The light we see is old, but the galaxy itself has aged alongside us. At the edge of the observable universe, time flows just as it does here. Clocks tick, stars burn, galaxies evolve. The distance is vast, but the present moment is shared. In this sense, the entire universe breathes together, even if we can only see its past. The universe might repeat in cycles. Some cosmological models propose that the universe doesn't have a single beginning and end. Instead, it cycles. After expanding for trillions of years, it might contract, collapsing back into a hot, dense state, then rebounding into a new expansion. Each cycle would erase most traces of the previous one, but subtle patterns might survive, encoded in the structure of space or the distribution of matter. If this is true, the edge we see now is just the edge of this cycle. Before it, there were others. After it, there will be more. The universe becomes eternal, not by lasting forever, but by beginning again and again. An endless rhythm of birth, growth, collapse, and rebirth. The edge, then, is not an ending, but a turning point, a place where one chapter closes and another waits to begin. Neutrinos from the edge pass, through us unnoticed. Right now, neutrinos from the most distant galaxies are passing through your body. These ghostly particles barely interact with matter. They can travel through entire planets without touching a single atom. Neutrinos are produced in enormous numbers by stars, supernovae, and the early universe itself. Some of them have been traveling since the universe was young, crossing billions of light years to reach us. We've built massive detectors to catch a few, but most slip by unnoticed. They carry information from regions we can't observe with light. In the future, neutrino astronomy may reveal secrets hidden at the edge, events too faint or too distant for photons to reach us. For now, they pass in silence, messengers from the farthest reaches, invisible and patient. The speed of light sets the ultimate limit. Nothing can travel faster than light. This isn't just a rule. It's a fundamental property of space-time. Light moves at 299,792,458 meters per second, and that speed is the maximum at which information or matter can travel through space. This limit defines the edge of what we can know. We can't send a signal faster than light, and we can't receive one that hasn't had time to reach us. The observable universe is bounded by this speed. Everything beyond the cosmic horizon is cut off, not by walls, but by the geometry of space-time and the finite age of the universe. The speed of light is the speed of causality itself, and at the edge, that speed becomes the line between the knowable and the unknowable. The universe could end in fire or ice. Cosmologists have imagined many fates for the universe. In one scenario, the Big Rip, dark energy grows so strong that it tears apart galaxies, stars, planets, and eventually atoms themselves. In another, the Big Crunch, gravity overcomes expansion, and everything collapses back into a singularity. A third possibility is heat death, where the universe expands forever, cooling and darkening until all energy is evenly distributed and nothing can happen anymore. Each ending is different: fire, ice, or silence. But all share one truth: the edge of the universe will change. It will grow, shrink, or fade. The cosmos is not static. It's evolving towards something, even if that something is stillness. And at the end, whatever form it takes, the edge will be the last thing to go. Some galaxies are already beyond our reach forever. There are galaxies we can see now that we will never be able to visit, even if we invented faster than light travel tomorrow. The space between us and them is expanding so quickly that they've already crossed a threshold called the cosmological event horizon. Any signal we send will never catch up. The gap grows faster than we can close it. These galaxies are not gone. They're still there, still shining. But they exist in a part of the universe that's causally disconnected from ours. We can observe them, study their light, learn from their past, but we can never touch them, send a message, or meet anyone who lives there. They drift away, slowly fading from view, becoming fainter and redder until they slip beyond detection entirely. The universe is not just vast, it's growing, and with each moment more of it becomes unreachable. The Planck length might define the smallest edge. If space itself has a structure, it might be made of something incredibly tiny. Units of distance called the Planck length. This is about 10 nanosecond and 35 meters, far smaller than an atom, smaller than anything we can measure. At this scale, space might be grainy or quantized, like pixels on a screen. If true, then the universe has an edge not just at its largest scale, but at its smallest. A boundary where smoothness breaks down into discrete chunks. We don't have the technology to probe this scale, and we may never will. But some theories of quantum gravity suggest it's real. The universe, then, would be bounded not only by distance and time, but by resolution itself. A cosmos with edges at both extremes, the infinitely large and the infinitesimally small. The universe's fate depends on dark energy. What happens to the universe depends on what dark energy is and how it behaves. If it remains constant, the universe will expand forever, cooling and darkening in a slow heat death. If it grows stronger, it could tear everything apart in a big rip. If it weakens or reverses, the universe might stop expanding and collapse. We don't know which will happen because we don't fully understand dark energy. It's the dominant force shaping the cosmos, yet it remains one of the biggest mysteries in physics. The edge of the universe is being shaped by dark energy right now. It's pushing galaxies away, stretching space, and determining the ultimate fate of everything. The edge is not fixed. It's being written by forces we're only beginning to comprehend. Ancient stars near the edge hold clues to the beginning. The first stars were very different from the Sun. They formed from pure hydrogen and helium, with no heavier elements because none existed yet. These stars, called population 3 stars, were massive, hot, and short-lived. They burned bright and died young, exploding as supernovae and scattering the first heavy elements into space. We've never seen one directly. They all died long ago, but near the edge of the observable universe, we might find their remnants or the galaxies they helped create. Observing these ancient systems gives us clues about the universe's earliest moments. The edge is not just a spatial boundary, it's a temporal one, a window into the past. And in that past, hidden in the light of distant galaxies, the story of the first stars waits to be read. The universe expands, but galaxies don't. It's a common misconception that everything in the universe is expanding. It's not. Galaxies, stars, planets, and even atoms remain the same size. Only the space between galaxy clusters is growing. This is because local gravitational forces hold galaxies together, easily overcoming the gentle expansion of space. The Milky Way and Andromeda are actually moving toward each other, not apart, because gravity pulls them together. Expansion only dominates at the largest scales, where galaxies are too far apart for gravity to bind them. At the edge of the observable universe, this expansion is most apparent. Distant galaxies race away, carried by the stretching of space itself. But here, in our local corner, we're held in place, anchored by gravity, while the cosmos around us grows. Light can orbit a black hole before escaping. Near the edge of a black hole's event horizon, space-time is so curved that light can orbit in a circle. This region is called the photon sphere. If light is aimed just right, it can loop around the black hole multiple times before either escaping or falling in. This creates strange optical effects. You could, in theory, see the back of your own head if you were in the photon sphere, though you wouldn't survive the journey. Black holes warp space so dramatically that even light, the fastest thing in the universe, can be trapped in orbit. At the edge of these objects, reality bends in ways that challenge our intuition. The edge of a black hole is not like other edges. It's a boundary where the rules change, where time slows, and where even light struggles to escape. The observable universe is a sphere around us. When we talk about the observable universe, we're describing a sphere. We sit at the center, and the edge is about 46 billion light years away in every direction. This sphere is defined by the distance light has been able to travel since the Big Bang. It's not a physical bubble, it's a bubble of information. Everything inside it can be observed, in principle. Everything outside it cannot. But this sphere is unique to us. Every observer in the universe has their own observable sphere, centered on their location. A distant alien would see a different set of galaxies. Their edge would not be ours. The universe doesn't have one edge. It has as many edges as there are observers, each one creating their own horizon, their own boundary of light and knowledge. The universe's earliest light took 13 billion years to reach us. The cosmic microwave background is the oldest light we can see. It was released when the universe was just 380,000 years old. But that light has been traveling toward us for over 13 billion years. In that time, space has expanded dramatically. The region that emitted the light is now much farther away than 13 billion light years. It's about 46 billion light years away. Due to the expansion of space during the light's journey, this means the edge of the observable universe is not determined by age alone, but by the combination of time and expansion. The light we see now is ancient, but the source has moved on. The edge is not where things were. It's where they are now, carried by the tide of cosmic growth. Some regions of space are causally disconnected from us. Causality means cause and effect. For two events to be causally connected, a signal must be able to travel between them at or below the speed of light. But in an expanding universe, some regions are so far apart that no signal can ever connect them. They exist in the same universe, but they can't influence each other. They're causally disconnected. This happens beyond the cosmological event horizon. Galaxies on the other side of that boundary will never receive light or signals from us. We'll never receive anything from them. They're part of the universe, but not part of our future. The edge, in this sense, is a line drawn by causality itself, a boundary not of space, but of connection. Gravitational lensing lets us see beyond the edge. Sometimes gravity bends light so much that it acts like a magnifying glass. When a massive galaxy or cluster sits between us and a more distant object, its gravity warps the light passing by, focusing it toward us. This is called gravitational lensing. It allows us to see galaxies that would otherwise be too faint or too far away. In some cases, we can observe objects that are effectively beyond the edge of what our telescopes could normally detect. The lens brings them into view, brightening and distorting their image. It's a natural telescope provided by the universe itself. At the edge, where light is faint and ancient, gravitational lensing is one of our most powerful tools. It lets us peek a little further, see a little deeper, and glimpse what lies just beyond the boundary. The edge of the universe was once closer than the moon At the moment of the Big Bang, the entire observable universe was compressed into a space smaller than an atom. The edge, such as it was, would have been unimaginably close. Within the first second, the universe expanded to the size of our solar system. Within minutes, it was light years across. Today, the edge is billions of light years away, but it was once within arm's reach. This rapid growth is hard to comprehend. It means that particles now separated by vast cosmic distances were once so close they could interact. The matter making up distant galaxies and the matter in your body were once touching, part of the same hot, dense plasma. The edge has grown, but the connection remains. Everything in the universe shares a common origin, a single moment when all distance was zero. Some galaxies are dim because they're made of dark matter. Most galaxies shine because they're full of stars, but some galaxies seem to contain very few stars relative to their mass. These dark matter-dominated galaxies are faint, almost invisible, detectable mainly through their gravitational effects. They're not at the edge of the universe, but they remind us that much of the cosmos is hidden. At the true edge, beyond what we can see, there may be entire structures made mostly of dark matter, galaxies that never formed stars, or systems too dim for us to detect. The universe may be far richer and more populated than our observations suggest. The edge we see is the edge of light, but the edge of matter might lie much further, in regions too dark to observe, too faint to illuminate, and too distant to ever know. The cosmic microwave background is cooling. When the cosmic microwave background was first released, it had a temperature of about 3000 Kelvin. Today, due to the expansion of the universe, it's cooled to just 2.7 Kelvin. As space continues to expand, this radiation will cool further. In the distant future, it will drop below 1 Kelvin, then lower still. Eventually, it will become so cold and faint that it will be nearly indistinguishable from the background of space itself. The universe's first light will fade into invisibility, a relic so ancient and stretched that it can no longer be detected. The edge of time marked by this glow will disappear, not because it stopped, but because it became too cold, too faint, too quiet, and the universe will lose one of its oldest memories. The universe might have edges in higher dimensions. Our universe has 3 dimensions of space and 1 of time. But some theories, like string theory, suggest there are more dimensions we can't perceive. These extra dimensions might be curled up, tiny and hidden, or they might extend in ways we can't detect. If they exist, the universe might have edges in those dimensions, boundaries we can't see or reach because we're confined to 3-dimensional space. It's like a fish in a pond, unable to perceive the surface above or the air beyond. The edge of the universe in this view isn't just out there in space. It might be perpendicular to everything we know, invisible and unreachable, a boundary in a direction we can't point to or imagine. Every galaxy will eventually be alone. Because the universe is expanding and accelerating, galaxies are moving apart. In the distant future, billions of years from now, galaxies beyond our local group will have receded so far that their light will no longer reach us. The night sky will darken. Eventually, only the galaxies bound to us by gravity will remain visible. The Milky Way, Andromeda, and a few smaller companions will merge into a single giant galaxy. And around it, nothing. No distant stars, No clusters, just darkness. Observers in that future era will see a universe that appears small and empty. They won't know about the vast cosmos beyond, because all evidence will have slipped past the edge of observability. The universe will seem lonely, and in a sense, it will be. Each galaxy, an island in an ever-growing ocean of darkness. The universe's expansion has no center. When we say the universe is expanding, it's natural to imagine it growing from a center, like a balloon inflating. But that's not quite right. The expansion has no center. It's happening everywhere at once. Every point in space is moving away from every other point. If you were in a distant galaxy, you'd see the same thing we see. Everything receding in all directions. There's no special location from which the expansion originates. The Big Bang didn't happen at a place. It happened everywhere. The edge, then, is not the boundary of an expanding sphere. It's the horizon of visibility, a sphere that surrounds every observer, no matter where they are. The universe has no center and no edge in the conventional sense. It simply is, growing in all directions equally, without preference or origin. Dark matter might form invisible structures at the edge. Dark matter doesn't emit or absorb light, so we can't see it directly. But we know it's there because of its gravitational effects. It makes up about 27% of the universe's total mass energy. At the edge of the observable universe, dark matter may have formed structures we'll never see, halos, filaments, and clumps that contain no stars at all. These invisible architectures shape the cosmic web, guiding where galaxies form and how they move. But in regions too distant for light to reach us, dark matter might dominate entirely, creating a hidden landscape of gravity and mass. The edge we observe is a boundary of light, but the edge of dark matter could extend further, shaping regions we can't see, influencing the cosmos in ways we can only infer. Some scientists think the universe might be flat. The shape of the universe is determined by its density and the curvature of space. If the density is exactly right, the universe is flat, meaning parallel lines never meet and space extends infinitely in all directions. Current measurements suggest the universe is flat, or very close to it. This doesn't mean it's a two-dimensional plane. It means the geometry of space is Euclidean on the larger scales. A flat universe has no edge. It goes on forever, but we can only see a finite portion because light has only had a finite time to travel. The flatness of the universe is one of the great puzzles of cosmology. Why is the density so precisely balanced? The answer may lie in inflation or in deeper principles we don't yet understand. The universe's background hum is always there. The cosmic microwave background isn't just an image. It's a signal, a faint hum of radiation that fills all of space. If you could tune a radio to the right frequency, you'd hear it, a soft static underlying everything. About 1% of the static on an old analog TV comes from this ancient light. It's everywhere, uniform and ever-present. At the edge of the universe, this hum is the same as here, a faint whisper from the beginning of time. It doesn't change, it doesn't fade except slowly. Over billions of years, it's the universe's oldest song, a quiet note that's been playing since space first cleared, since atoms first formed, since light first traveled free. And it will keep playing, softer and softer, until it fades into silence. Time dilation affects observations at the edge. According to general relativity, time flows differently depending on gravity and velocity. For distant galaxies moving away from us at high speeds, due to the expansion of space, time dilation effects come into play. Events in those galaxies appear to happen more slowly from our perspective. A supernova that takes days to brighten and fade would appear stretched in time if it's far enough away. This doesn't mean time actually moves slower there. It's an observational effect, a consequence of the expanding universe and the finite speed of light. At the edge, these effects become significant. Time itself seems to stretch, blending with the stretching of space, creating a strange symmetry where distance and duration are woven together into the fabric of observation. The universe has no preferred direction. When we look at the universe on the larger scales, it appears the same in every direction. This property is called isotropy. No matter where you point your telescope, you see roughly the same number of galaxies, the same cosmic structures, the same background glow. There's no preferred direction, no axis, no special orientation. This suggests the universe is homogeneous and isotropic, uniform on large scales. But small deviations exist. Tiny ripples in the cosmic microwave background, slight variations in density. These ripples are the seeds of galaxies, the fingerprints of quantum fluctuations stretched to cosmic size. The edge appears the same in all directions, but subtle differences tell the story of how structure formed, how the universe grew from smooth to complex, from uniform to varied. Quantum fluctuations may have shaped the edge. In the first moments after the Big Bang, the universe was so small that quantum effects dominated. Tiny random fluctuations in energy and density appeared and were instantly stretched to enormous scales by inflation. These quantum ripples became the seeds of galaxies, clusters, and the cosmic web. In a sense, the edge of the universe was shaped by randomness, by the uncertainty built into the fabric of reality at the smallest scales. What began as quantum noise became cosmic structure. The edge we see today, the distribution of galaxies, the shape of voids and filaments, all trace back to those first fluctuations. The universe's largest features have their roots in the smallest possible events. A strange and beautiful connection between the quantum and the cosmic. The universe might have collided with another. Some cosmologists speculate that our universe might have collided with another universe in the distant past. If true, this collision could have left traces, anomalies in the cosmic microwave background, unexpected patterns, or cold spots. One such anomaly does exist, a region of the sky that's colder and larger than expected. Could it be the scar of a cosmic collision? We don't know. The evidence is not strong enough to confirm it, but the idea remains tantalizing. If other universes exist, and if they can touch, then the edge of our universe might not be empty space, but a boundary between bubbles of reality. What we call the edge might be a meeting place, a point of contact between separate cosmoses, forever beyond our reach, but forever shaping what we see. Infinity might be real. Mathematicians are comfortable with infinity. It's a concept, a tool, a way to describe endless processes. But is it real? Does the universe actually contain an infinite amount of space, matter, and time? Current observations suggest it might. If the universe is flat and has no curvature, it extends infinitely in all directions. There's no edge, no boundary, just more universe forever. This is difficult to grasp. Infinity is not just a very large number. It's a qualitative difference. An infinite universe means every possible configuration of matter occurs not just once, but infinitely many times. It means there's no edge to reach, no final frontier, just endless continuation. The edge we observe is not the end. It's just where our vision fails. Beyond it, infinity waits. The last star will burn out in trillions of years. Stars don't last forever. Even the longest-lived red dwarfs will eventually exhaust their fuel. Current estimates suggest the last stars will burn out in about 100 trillion years. After that, no new stars will form. The universe will enter an era dominated by black holes, white dwarfs, and brown dwarfs. These remnants will glow faintly with leftover heat, slowly cooling over unimaginable timescales. At the edge of time, the universe will be dark and cold. No starlight will shine. No planets will orbit glowing suns. The edge of the stellar age will give way to the age of remnants, a long, quiet twilight that stretches toward entropy. But even in that darkness, structure will remain. Gravity will still act, and the universe, though changed, will endure. Hawking radiation could make the universe end with light. In the far future, after stars have died and galaxies dispersed, black holes will dominate the universe. But even they won't last forever. Through Hawking radiation, black holes slowly lose mass, emitting faint streams of particles over trillions of years. As they shrink, the radiation intensifies. In the final moments, a black hole evaporates completely, releasing a burst of energy. If this process is real, and most physicists believe it is, then the universe's final act might be a slow rain of light. One by one, black holes will evaporate, returning their mass to the cosmos as radiation. The universe will end not in darkness, but in a faint, diffuse glow. The last photons are the last black holes drifting through infinite space. We are witnessing ancient light. Every night, every time you look at the stars, you're seeing the past. Light takes time to travel. The sun's light takes about 8 minutes to reach Earth. The nearest star, Proxima Centauri, is over 4 light years away. Distant galaxies are millions or billions of light years away. When you observe them, you're seeing that they looked like millions or billions of years ago. At the edge of the observable universe, we see galaxies as they were over 13 billion years ago, shortly after the Big Bang. The night sky is not a snapshot of the present. It's a collage of different times, layered by distance. The edge is the oldest layer, a window into the universe's earliest ages. Every photon carries history, and the further we look, the deeper we travel into time. You are connected to the edge. The atoms in your body were forged in stars. Those stars formed from gas and dust that was once part of the early universe. That gas was shaped by the same forces that created the structures we see at the edge. You are made of the same matter that fills the cosmos, governed by the same laws, born from the same beginning. The edge may be distant, but it's not separate. It's part of the same story. The universe is a whole, and you are a piece of it, a conscious fragment looking back at the vastness from which it came. The edge is not just out there. It's in you, in your history, in the elements of your body, in the breath you take. You are the universe aware of itself. And in that awareness, the edge comes home. The universe is still writing its story. The edge of the universe is not fixed. It moves, changes, and evolves with time. New light arrives. Old light fades. Galaxies drift beyond reach. Others merge and transform. The cosmos is not a finished canvas. It's a work in progress, unfolding across eons. What we see now is just one chapter in a story that began 13.8 billion years ago and may continue for trillions more. The edge marks the boundary of the known, but also the beginning of the unknown. Beyond it lies mystery, possibility, and perhaps infinity. We don't have all the answers. We may never will. But the questions remain, glowing softly at the horizon, inviting us to wonder, to explore, to imagine. The universe is vast, and its edges, whether real or conceptual, remind us of how much there is still to discover. And now, as we reach the edge of this journey together, let the vastness settle around you like a blanket. We've drifted through cosmic horizons, ancient light, and infinite possibilities. We've touched a boundary between the known and the unknowable, stood at the threshold where light meets darkness, where time meets timelessness. The edge of the universe is not a wall or a cliff. It's a gentle fading, a horizon that recedes as we approach, a boundary drawn by light and time. And perhaps that's fitting. Perhaps the universe doesn't end sharply but softly, like the way sleep arrives, not all at once, but in gentle waves. You've traveled so far tonight, across billions of light years, through the history of everything. And yet, you've never left this moment, this breath, this quiet space where you rest. The universe is vast beyond comprehension. But it's also here, in the atoms that make you, in the light that reaches your eyes, in the thoughts that drift through your mind. The edge is distant, but it's also close. It's the boundary of what we can see, but also the invitation to imagine more. So let yourself rest now. Let the cosmos hold you. Let your thoughts drift like photons through expanding space, soft and unhurried. Somewhere at the edge, light is still traveling, stories are still unfolding, and the universe is still breathing. You are part of that breath, part of that light, part of that story. And for tonight, that's more than enough. Sleep well, traveler. The universe will still be here when you wake. Vast, mysterious, and waiting. And if you'd like to drift through more cosmic wonders, consider subscribing. There are always more journeys to take, more questions to ponder, more quiet corners of the cosmos to explore. But for now, rest, dream gently, and let the edge of the universe carry you softly into sleep. Good night.